Yes, Darshita, please go ahead.
Okay. So, good afternoon, students. So, today we are going to synthesize methyl orange. So, as you know, methyl orange is an indicator. So, it's very important indicator for acid-base titration. So, its distinct color in acid is orange or red in color, and in base it is yellow in color. Though it does not give a range of color in between, but for acid base titration, this is very important. And another thing is that we can use this methyl orange as a dye for in our dyeing industry in other purposes. So for synthesis of methyl orange, so what we need sulfonuric acid and N dimethyl aniline. And by reaction type, this is basically a coupling reaction. So first we'll synthesize the diazonium salt, and then we'll couple the diazonium salt with N dimethyl adenine to prepare that methyl orange. And for synthesis, this is very easy, but there are very crucial steps as this is a diazotization reaction, as you know. So what we have to do, we have to take 0.5 gram Na2CO3 sodium carbonate, and we have to dissolve it in 20 ml of water. So why we need Na2CO3? As you have seen, that the sulfonuric acid, that is para-aminobenzene sulfonic acid, so it's an organic acid, though it's appear in Jupiter ionic form, but still it is insoluble in water. So to make it soluble in water, we need to make this OH to ONA, corresponding sodium salts, and that's why we need sodium carbonate. So we will dissolve that sodium carbonate in 20 ml water in a beaker, and we will add 2 gram pure dry sulfonuric acid and make a homogeneous solution. We will completely dissolve the sulfonuric acid. If it is required, we will warm it little bit so that the entire sulfonuric acid dissolve in that sodium carbonate solution. And then once it dissolve, we will add 0.5 gram NaNO2 solution, and in 5 ml water. So we'll take 5 ml water, we'll dissolve 0.5 gram NaNO2, make a clear solution, and then we'll add this to this sulfonuric acid solution. And this solution we will cool at 0 to 5 degrees centigrade by placing on ice cold water. So for coupling reaction, or the before coupling reaction, it is a diazotization reaction. For diazotization reaction, this temperature is very important. So we will maintain the temperature from 0 to 5 degrees centigrade by placing the reaction mixture on ice cold water. So once the solution is cool, then we will add cold solution of 1 ml concentrated HCl. So we will take 1 ml concentrated HCl in 10 ml water. So that solution we will prepare previously. We will put that solution also in ice cold water, and we will make that solution cool, and we will add that acid to this reaction mixture. So once we add that acid to this reaction mixture containing NaNO2, they will react, NaNO2 and HCl will react to prepare that HNO2, and that will act as the diazotizing agent. And then the diazotization will take place, so we'll see a color change is happening. And once that have done, so we'll add 1 ml N dimethyl aniline in 1 ml glacial acetic acid. So N dimethyl aniline, so that is liquid, and we'll make a solution of N dimethyl aniline in glacial acetic acid and 1 ml water, and we will also cool that solution and at 0 to 5 degrees centigrade ice water bath, and we will add that to that reaction mixture. And so immediately the coupling reaction will take place, and we'll see the color changes from its previous diazotization color to now the methyl orange color. And we'll allow the mixture to stand for 15 minutes and to complete that coupling reaction. and then we'll make it alkaline, the reaction mixture. So we have added HCl, we have added glacial acetic acid. So now we need to make the reaction mixture alkaline by addition of 20% aqueous sodium hydroxide solution. Okay, and then in our solution we have methyl orange, but now it is as a sodium salt, and so this will be soluble in that solution. So we need to precipitate it out. For that purpose, we will heat the reaction mixture for 80 to 90 degrees centigrade for few minutes, and then we will add 1 gram of sodium chloride. So the sodium chloride, so once we add sodium chloride, due to common ion effect, that methyl orange will now precipitate out of the solution. And so we'll collect and filter the precipitate of methyl orange solution and wash with cold water and recrystallize from boiling water. So now Sumon will show you the reaction mechanism. So that is the how we can synthesize this methyl orange, and now Sumon will show you the reaction mechanism.
Yeah, thank you, Dasda. So I'll share the Jamboard. Present screen. Okay.
Yes,
Is it visible? Visible,
yeah,
right?
yeah, it's visible.
So students, I gave access to you. You can also edit. But don't edit unless I ask. Let us select this yellow ink. Okay. Mechanism is a coupling reaction. So here the thing is, it's quite similar, or there is some similarity of with this coupling with what we have done during nitration. You remember during nitration, we have generated one activated electrophile. It was the NO2 plus ion, and that immediately reacted with the aromatic system, and it gave the dinitration there. In this case also, you will see will generate initially one reactive intermediate, and that will eventually react with the aromatic system, not really aromatic system, with the present nucleophile present there, and then it's form another reactive intermediate, and ultimately the coupling will go on. So let us instead of organic chemistry, is better to explain with structure rather than just by saying. So what's happening here, as Professor Haldar also already mentioned, we have NaNO2 and we are adding HCl. Okay. Once you have HCl, immediately it will form HNO2. Okay. And if we expand the structure of HNO2, it's like this. We have NO and OH. Okay. We have in this, if you check the procedure, we have added enough acid, so more protons are around. So with oxygen, with a couple of lone pairs of electron, will immediately catch one of the protons here and becomes OH2 plus, which is ready to leave. Okay. Once this guy leaves, you can see nitrogen lost the bond pair, so it forms NO plus. In nitration, we had NO2 plus. In this case, it's NO plus. It's a bit similar but different. But this NO plus, you see this nitrogen do not have octet field there, because only 6 electron. Nitrogen, of course, is having a lone pair of electron, and from these two bonds getting 4 plus 2, 6 electrons, octet is not filled. So, but this oxygen will feel the pain of nitrogen and can donate one pair of electron with this resonance. Okay, although now oxygen becomes plus, this resonance structure is more stable, because here all the both the atoms are having field octet. But anyway, this NO plus is an reactive electrophile. Okay, and if you check the procedure, what we added there, this acid, that acid with amine group present, NH2, and as Professor Halda mentioned, just to make it dissolve, we have make a sodium salt, NaO. Okay. So now onwards, because it's a big group, just to make it easy, we'll just designate this as aryl group. So,
Hello, sir.
yep.
Sir, can't we do reaction in, organic solvent? We are choosing water.
Organic solvent
The
generally, yeah.
main purpose of sodium carbonate is to make it dissolve. Make it inorganic compound so that it will dissolve in water, inorganic solvent, and the further reaction can be proceeded.
But in this case, you see, the problem is we are using inorganic acids, no? This salt and inorganic acids. So there also will have problem to solubilize in organic solvent. This NaNO2 is not soluble in common organic solvents. Okay. HCl is rather okay. It's some dioxin or so. You can manage HCl, but NaNO2 will not be. It's a pure inorganic salt. Okay. But this guy just making a salt, we can dissolve it. So because you are doing a reaction between an organic reactant with inorganic thing, so it's better to choose one. So with in this particular case, this is much easier to make it soluble in water. And also, water is more greener and cheaper compared to organic solvent. So if there is a option to do it in water, better to go for water. All right. Okay, so now onwards we'll write it's like Ar, just to make it easy to write ArNH2. So ArNH2, this nitrogen is having a lone pair of electron, which can be a good nucleophile, which will just react with here. So what will form Ar N, you see, N O. We have two options. We can make this nitrogen plus, or so the release of proton later. So we'll go for this. So it's like this initially, but then one by one this guy will lose protons. It's just a follow-up steps of releasing and taking protons like this. Let us go this side. Ar N. Now you see, as a nitrogen double bond comes here after these steps, and this becomes OH. Okay. Nitrogen is still plus, and one more proton is going there, and this is taking another proton, so ultimately forming the water. And what happened in this part, Ar nitrogen is still plus, okay, because it's just after releasing this proton, it's making this bond pair is just shifting here, so charge on nitrogen is not changing. But what happened, so it was two bonds here, it becoming three bonds between two nitrogens and plus. That's the desired intermediate, that's the diazonium salt, where nitrogen, the middle, this nitrogen is having four bonds and with a plus charge. So we initially added HCl, so we can write that the counter anion, any cation must be having a counter anion. So this is the salt. But in water, it will be dissolved. Basically, it will be surrounded with both the anion and cation will be surrounded with water molecule just to solubilize. Okay, so just by doing this reaction, mixing NaO2, HCl, and this amine can generate the diazonium salt. As Professor Halder, if you keep in mind that as Professor Halder mentioned, this diazonium salt is not very stable. It has relative stability, but not very stable. So if its temperature goes up, there is always a possibility that this N2 will really go out as nitrogen, dinitrogen. Okay, and then because dinitrogen is a very stable molecule, if you get fragmented, the entropy advantage is there, and form the aryl radical here, and then it goes out as dinitrogen. All right. So that's why but we don't need it. We want to incorporate both the nitrogen in the next steps. We need to keep the temperature lower, always below 5 degrees Celsius. So once we have this diazonium salt ready, so we'll add the other coupling partner, so which is the NN dimethylamine. Here, amine. So as I explained that day several times, that this aromatic ring is quite activated because of the plus M effect of this nitrogen. Okay, and this electron-rich aromatic system, so now can act as a nucleophile, and you can see this is because this nitrogen is positive, any cation is lacking of electron, right? So that can be a good electrophile. Same here, right? So it's similar. NO plus also good electrophile. Here diazonium salt also can be a good electrophile. And now there is a possibility that this guy can react through these ortho positions and also through para position. Is ortho para directing, right? So as you know, it's electron rich group, it's ortho para directing. But you can already imagine that this methyl groups is tetrahedral, it's blocking these ortho positions. So rather it will prefer to go for the para one. Same like this acetanilide bromination when we did, right? Same logic. So this will donate electron and it will preferably go to para. It will react on this nitrogen. So then after a long time, this nitrogen get back this lone pair. Okay, so through all the steps, it was lacking that, always positive. So once this electron reach aromatic system, donate electron or react with them, form a bond, it gets back the ultimately electron and forming our this product AR nitrogen. Triple bond becomes double bond here. Take a little bit less space here, but anyway, oops, we'll manage. Two methyl groups here plus here. Last step is nothing but rearomatization, like this, and it will form the methyl orange. I will draw it like this. It's fully aromatized now in Me2. Okay, so this is the ultimate compound. Now you can imagine, you can see how the color is coming. You see, any dye is giving absorbing light in visible region will give color, right? And this is only possible when there is a long elongated conjugation. So we have synthesized this indigo dye. There also we have seen is it was a long conjugation, so that the homolupo gaps becomes relatively less, and there can be an easy electronic transition just by absorbing visible light between 400 and 800. Same here. So this, because of this long conjugation, you see from here to here to here to ultimately I haven't drawn this SO3 group. It goes up to the SO3 group, SO2 SO3 H group, okay, of this aromatic ring. So from starting from this terminal, it can go all the way to the other terminal, the electron flow. So that's why it can give a very good color, as Professor Halder mentioned. So it, with the variation of pH below around 3.5 to 4, it gives red color, and above it gives yellow color. And it's a very good application. This particular dye having a very good application in acid base as an indicator of acid base reactions. So it's nothing very complicated, just to stepwise, as I mentioned. Initially, we generated one activated electrophile, then it reacted with the nucleophile, and ultimately with this sequence, this becomes the coupling between HNO2 or NO plus rather, and this amine group makes the another electrophile, which is the diazonium salt. And once the diazonium salt is ready, then we added the NN dimethyl aniline, which is another nucleophile, and then ultimately this coupling between two fragments, aromatic fragment happens, and we gives this beautiful dye. Okay. So any question on the mechanism? If not, then we'll go back to you, Debasista. And yeah, okay. So there is one question. Just a moment. I will stop sharing my screen. Maybe. Okay. Okay, sure. Why did we add NOH and make the solution basic? So you mean afterwards, right, Madhur? Afterwards or initially? We
Shuman, it
did it.
is afterwards.
Yeah. Initially, Devasith sir already said to make it solubilized, right? And afterwards, sir also mentioned that special ion effect. No, sorry, just to need to quench the thing, right?
Yeah. Shuman,
Yeah,
I am saying.
yeah. Okay,
So,
please go ahead.
so what we have done, we have made the reaction in acidic condition. So that is in HCl. And once we use HCl and this dimethyl aniline form, in presence of excess HCl, as the reaction medium is acidic, the NN dimethyl, that nitrogen will now be protonated, and that will form that protonated amine, and so it will be completely soluble in water. So you cannot take out that dimethyl methyl orange from the water now. So first we need to make it alkaline to make that amine free from that proton, and so we will add NaOH to make it alkaline. So our acid part, sulfonic acid part, is already in salt form. So we need to make that amine free from that proton, and now it will come out of the solution. And to better precipitation, we will add more sodium chloride, and that will help as a common ion effect to precipitate out this dye from water medium. Okay, so any more questions?
Hello, sir.
Yes, please.
Sir, we prepared the 1 ml of aniline in glacial acetic acid. Why did I mean in acid only?
1 ml of aniline is glacial acetic acid, because so glacial acetic acid is a solvent that can mix with water also. But if we add just N and dimethyl aniline in water, it will not dissolve in water. So that's why we prepare a solution of N and dimethyl aniline in glacial acetic acid. And now that solution we added to aqueous medium, aqueous reaction mixture, and everything now dissolve.
So we need an acid which will be soluble in water, and also it will solubilize in N-dimethyl aniline. Okay, so that
Sir,
perfect balance. Yeah,
why
so
the solution was heated to 80 to 90 degrees Celsius at last? I mean, after 15 minutes, we trapped it and then we heat the solution to around 80 to 90 degrees Celsius.
just to make sure all the reaction happens.
So we are doing the reaction in 0 to 5 degrees centigrade. That is quite low temperature. But you know, for every reaction there we need an activation energy. So once we want to complete the reaction, and that's why it was heating at the end.
Okay, so should I do the share the video now, Devasita?
Yes, please, if there is no more question.
So will you please repeat that part, that why are we heating the reaction mixture to 80-90 degrees?
So we have done that diazotization reaction at 0 to 5 degrees centigrade to keep the NO2 plus in solution. And then the coupling reaction we have done. To complete the reaction, we need some more activation energy. So at the end, we are heating the reaction mixture at 80 to 90 degrees centigrade. So the reaction should be complete. Otherwise, it will take a very longer time to complete the reaction.
But it won't serve the purpose, because the completion of the reaction means the formation of more NO plus.
Methyl orange. No, methyl orange.
But methyl orange itself requires low temperature for synthesis. Means
Yes,
won't
so,
the reaction go backward if we heat it?
So that part we have already done.
Ji?
So we are heating after addition of N and dimethyl aniline in cold condition. Then we have spent some 15 minutes with continuous stirring to continue the reaction. And at the end, we are heating the reaction mixture to complete the reaction.
No, look, see, basically when you mix both, no, so initially the reaction is happening, but concentration of the reactants are high. So
Mm,
with time when the reactants, that basically the diazonium salt and NN dimethyl aniline is getting consumed, the concentration is getting low, right? Concentration is
mhm,
getting low, 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 and when suppose only 5-10% is remaining, so most of them are
mm,
converted into product, only 5-10% reactants are remaining, then you imagine there, so more in the solution most of them are product, right? And this is because is a bimolecular coupling, is collision required between to
uh-huh,
have, yeah,
yes.
between these two, dimethyl aniline and diazonium salt. But because this, when only 5-10% remaining, the probability of collision is getting less, right? So reaction is getting slow, the effective reaction is getting slow. Okay,
Mm,
so at the end, this little heating for short time makes sure that this effective collision is happening. Okay, if we increase the temperature, of course the kinetic energy will increase and collision will increase, and this last 5-10% to make sure everything goes reacts, so we are heating. All right, initially we don't need it, because initially if we start heating from the very first minute, so what will happen, there is also a possibility that this diazonium salt can decompose
mm,
initially. Yeah. So suppose less 5% remains and then we heat it up. Okay, maybe 3% gives us some product, our desired product, and 2% get decomposed. Okay, then we don't
mm,
care. But initially, if you think that started heating from the first minute, then out of so if we suppose, let's say for easy calculation, so that 5% out of 5%, 2% decomposed. But initially, if we start that, so 5% is now 100%, 100%. So
40%.
that will be, yeah, 40% will get decomposed, right? So we
Mm,
don't want that, yeah. But that's why you understood, no? The last few percentage just to make sure. Otherwise, we have to
mm.
run it for a really long time. Yeah,
Thank you, sir.
yeah. All right. So I will share the video now. That screen.
Today we are going to synthesize.
Is it is it visible and audible? The video.
Yes, yes.
Okay.
Starting from sulfonilic acid. So inside the chemical hood, we have all the chemicals: sodium hydroxide, sodium chloride, sodium nitride, sodium carbonate, and sulfonilic acid. Also, we need dimethylanic and acetic acid, glacial acetic acid. So we have to weigh 2 gram of sulfonilic acid and 0.5 gram sodium carbonate. So sulfonilic acid being an organic acid, it is not completely soluble in water. It is sparingly soluble in water. To make the solubility better, we will dissolve it in sodium carbonate solution. So first we add 0.5 gram sodium carbonate in 20 ml water and make a sodium carbonate solution. 0.5 gram sodium carbonate in 20 ml water in a 100 ml conical flask. And we dissolve the sodium carbonate by stirring. So we will add 2 gram sulfonilic acid to this sodium carbonate solution. So you see the carbon dioxide is coming out.
Yeah, because it's an acid-base reaction, right? So that's why. CO2 came out. The acid of SO3H.
So we are adding 0.5 gram sodium nitrite. And we will cool this solution,
Yeah.
cool this reaction mixture at 5 degrees centigrade
Yeah.
for few minutes.
Because this HNO2 is also not very stable. Okay. So that's why we always prepare HNO2 from NaNO2 and adding acid. HNO3 is stable. Nitric acid you will get. But this nitrous acid, HNO2 is not available. Okay. Always in situ you have to prepare and at low temperature. Otherwise it will be too vigorous reaction. All right.
So in that meantime, we will prepare HCl solution, 1 ml HCl in 10 ml water. So first we will take 10 ml water and then we will add 1 ml HCl.
Yeah, commercial ACL is around 37%. If you calculate that, it comes around 10 normal. So if you dilute it by 10 times, 10 to 11 actually, that becomes 1 normal.
So this is the HCl solution, 1 ml concentrated HCl in 10 ml water. Simultaneously, we will prepare 1 ml dimethyl aniline solution in 1 ml acetic acid and 1 ml water.
Yeah.
1 ml acetic acid first we will take. With that, we will add 1 ml dimethyl aniline.
Yeah. In this reaction, we are dealing with reactive intermediates. Like first reactive intermediate is NO plus, and then the diazonium salt. Okay, so that's why two important thing is to keep the temperature low, and second is to mix the thing as soon as possible. Okay, so you see, Dr. Srikant, he made the HCl solution but did not add yet. Once you add, then you are initiating the reaction. Immediately NO plus will form and then it will react with amine and then it will form the diazonium salt. Okay. So before starting that diazotization process, he makes sure to make the other coupling partner ready to use. Okay, so that's why up to HCl he kept making the solution cool, and HCl, the glacial acetic acid and NN dimethyl aniline also is preparing. Yeah.
To that 1 ml glacial acetic acid solution.
Yeah.
With that, we will add 1 ml water and we will cool that solution at 5 degrees centigrade. So we are adding 1 ml water. So our aniline solution is now ready and we will cool it at 5 degrees centigrade.
We don't want to take any chance in the cold solution of diazodized salt. If we add something hot, oh, then it may also decompose some diazonium salt. That's why the acetic acid solution of dimethyl also were cooling. No? So both the cooled solution will um, mix. Yeah.
Okay. So now we will add that HCl solution we have prepared to the sulfonilic acid solution.
Yeah. We're all set now, ready to go. Now we are pressing the trigger. Yeah. Immediately reaction will start.
The diazotization reaction will take place, and immediately we will see a change of color.
See, it's getting brown. Yeah, you see? Yeah. Yeah, brown to red.
HCl to the NaNO sulfonilic acid.
Actually, everything was colorless. Should not add too fast. Then there will be reaction. Vigorous reaction may happen. Slowly, slowly you have to add.
So we have added HCl solution to the NaNO2 solution of sulfonilic acid. Diazotization takes place and the red color solution appears. With this solution, now we will add the cool N-dimethyl aniline solution in acetic acid.
Now, this diazotization is pretty fast reaction. It finishes within a minute. So it's ready now. We're adding the other coupling partner. Soon the intense color will come.
Red color
Yeah.
of methyl orange appear.
Yeah. It's too intense, right? It looks like black, but same like indigo. It's too concentrated. If it's when we'll dilute it, or we can during filtration, we'll see it's basically the red color. And because now it's acidic solution, right? We added HCl. The solution is acidic. That's why it's yeah.
Reaction for 15 minutes.
Yeah. The pH is acidic.
Now we are making the solution alkaline. So you see the methyl orange is red in color in acidic solution. And now we are adding 5% sodium hydroxide solution and making this reaction mixture alkaline. And now the color change from red to orange. Okay. For better precipitation,
we will add sodium chloride 1 gram. So due to common ion effect, sodium chloride will help to precipitate out the methyl orange from aqueous medium.
So there was a heating part at 80 to 90 degrees centigrade, but during edition of this video, so that actually removed. So it's a long process of heating, so we just removed that part. But there was a heating part.
So the bigger coagulation of methyl orange take place.
It's really a cocktail of salts. Many salts are there.
We filter the methyl orange using sintered funnel and aspirator. Now we are filtering the methyl orange through aspirator. Nice orange color precipitate, methyl orange appear. We'll wash it with cold water. We'll dry this methyl orange as much as possible, and then we'll go for the spectroscopic analysis. You can also decrystallize the methyl orange.
All right.
Okay, so if there any question,
I hope you understood the common ion effect nicely, right? So basically, as I said, it was a cocktail of salts in the solution, right? So, and this solvent, any solvent, a particular amount of solvent has the capacity to hold a certain amount of salts, right? So if you just take a glass of water and keep on adding sugar or whatever salt, after some time, the solution will become saturated. After that, whatever you will add, it will precipitate out, right? And now in this reaction mixture, it was in water, and then we did all the reaction, diazotization, blah, blah, blah. And then ultimately coupling happened. And because that the SO2 part is there, it's when we made it basic, it was still soluble in water. But now we really need to precipitate it out. Okay. But there are many other salts, like you remember initially we added sodium carbonate, then NaOH, and then HCl. So NaCl, blah blah. Many salts are there, and we want this particular salt to precipitate out. So if we just evaporate the, think about it, if we just evaporate the water using a rotary evaporator, what will happen? All the salt will become solidified. Okay. And that will be with methyl orange, all other salts will get. But we don't want that. We want only methyl orange to be precipitated out of the solution so that we can get it pure. That's why this common ion effect strategy we apply. So we add more sodium chloride there. Once we add more sodium chloride, so now there is a competition between this methyl orange salt and the sodium chloride salt, who will stay within the water, because once we add sodium chloride, so we are adding more salts, right? But as I said, water has certain capacity to hold the salts in within it, solubilize. Okay? After some time, it will become saturated. So now water has the option to release one of the salts. Okay, so water will release which one? That one that will be less soluble. So now think about it: competition between sodium chloride and this methyl orange salt. And chloride, sodium is common in both cases, but in one case the chloride, which is a tiny Cl minus, okay, and in this case methyl orange, it's a big organic part is there. And as you know, this water is a kind of ionic solvent which is very good in solubilizing salts. Okay, and chloride with a negative charge, a small salt, which is much more soluble in water compared to this methyl orange big organic part, because water don't like organic things. So that's why this, when we add more salt, rather the sodium chloride, added sodium chloride will go into the water, and this methyl orange part will precipitate out as a relatively pure thing. Also, little bit impurity will be there, some salt or whatever, some other unreacted things, but that we can purify easily by recrystallization. But major part, major junk salts will be stay in the solution. Okay, that's the thing. Yeah.
Yeah. So any other question, students? If no question, then I will show you the rest part of this presentation. So what rest we will do? So we have synthesized methyl orange, and we have filtered that methyl orange. We can recrystallize that methyl orange from boiling water. So you have to do nothing, only just place some amount of your synthesized methyl orange in a small beaker, add water and boil for few minutes. Everything will be dissolved, and just keep it on your desk. But as this is from water, you need to be patient at least for 2-3 days to get very nice needle shaped crystal, red color crystal. And for characterization, so once we got that methyl orange, so we can do the UV visual spectroscopy, FTR spectroscopy, fluorescence spectroscopy. As this is a color compound, we can see the emission spectra also and NMR. So this is the UV visual spectroscopy of the methyl orange. The red color solution of methyl orange. So when we have done the UV visual spectroscopy, we got two peaks at 275 nanometer and 500 nanometer. So you have to characterize the peaks responsible for what. This is the emission spectra of the compound. So you have to do a fluorescence spectroscopy, and it looks like that. And there are obviously few transition. This is the compound in trans form. So methyl orange, there is N double bond N, so it can exist in cis form and in trans form. So this is the spectra for trans form, but in cis form the spectra will change. So we are not showing that. This is the FTIR spectra of methyl orange. So here the characteristic peaks. You have many functional groups there, so you can identify the functional group and the peaks responsible for the functional groups. And this is the NMR spectra. We do not have various kind of protons, so only few of them. And as this is a salt, so we'll do the spectra not from CdCl3 but from DMSO-D6, dimethyl sulfoxide. So that is the NMR solvent. So we'll dissolve this methyl orange in dimethyl sulfoxide D6, and we take the spectra. And so this is the peak for water, and these are the peaks for the proton. So you just characterize this spectra, write in your laboratory notebook, and send back before the next practical day. Thank you.
Okay, guys, anyone having any question?
Yes, question? Yeah, anyone have any question? Or I will stop presenting. Okay. Yes. So any question? I have already incorporated this in your WLAN system. So you can check the PPT file from WLAN. The spectra walls are there. So you just need to write the peak position and the responsible system for which the peak appear in UV visible, in fluorescence, in FTIR, and also in NMR. And that's it.
Okay, so if they don't have any question, then I can stop.
Yes. So if you do not have any question, we are stopping here. Thank you.